My name is Mohammed Tarek, and in this lecture, we will explore and we will discuss about path compression. In the last lecture, we discussed and we created a set using some disjoint sets. We applied the unify method. We applied union on different disjoint sets, and then we created a new set. So we discussed in the last lecture that when we apply the unify method, when we apply the union method, that the result of the union method is a new set. We get a new set in which those disjoint sets become the part of that new set. Now, with that, we created a tree. We created a structure, a tree-like structure, and that structure was actually a set. And I also explained and showed you how this can be managed using arrays. So we managed all that process using arrays. Now we have a problem with that tree structure. And what is that problem? Let's first discuss that problem. And for the solution, we will apply the path compression technique. So here I have a tree. You can see a tree. This is actually a set. And these are the actual values, right? The values I showed you, that these are the actual elements, and these elements are represented by some numerical numbers, right? These are these numbers are actually representing these elements. These can be objects or anything. Here, for understanding, I have taken English alphabets, and this is an array. And these numbers that we are looking at, these numbers are the result of these operations, right? These union operations. After applying all these union operations, we got this kind of a set, and this tree is a physical, you can say a graphical representation of these operations. Now, what is the problem? So let's say if I want to find an element, so we know that every set has a name, has a representative. So here in this case, the representative of this set is A, right? Why? Because this is the root element, and it's not pointing to any other element. It's pointing to itself, and all other elements are connected to this element, the A element. So this is actually a set, right? This is a set, and this set can be called as set A, right? Why? Because this A is actually a representative of this set. So now if I say that I want to apply, or I want to find any element, right? So let me remove these union operations, because we have already discussed about these operations. Now I want to find an element. Let's say I want to find B, right? I want to find B. So what will be its result? Now let's try to understand this using this array, right? I'm not focusing, or I'm not using this tree structure. I want you to understand using this array. So let's say B. Where is B? The actual position of B is 1, right? Actually it was 1. We initially assigned 1 to the B. So let's go to the index number 1. So here is the index number 1. On index number 1, we will first check that the index and its value, is it equal? Because we need to know that is it a disjoint set, or B is a member of any other set, right? First we need to clarify this. Is B is a member of any other set, or B is a disjoint set, or B is a part of itself, right? It's a single element in a set. So when we compare these two values, we will know that the values are not equal. This means the B is a part of some set. So now the B is a part of some set. We will traverse to this number, right? We will go to this this index number. So at index number 1, we have a value of 0. So now we will go to 0, and this is the 0 index. So we made one hop. So here we made one hop, or you can say we took one step. So here I can say number of hops. Okay, number of hops. So let's say I have made one hop. Right now I made one hop. So now at index number 0, we will then again compare, are these two values equal? No, these two values are not equal. So now we will traverse, or we will take a step towards 6, index number 6. We will hop to index number 6. Now here is index number 6. Then again, so here is one more hop. We will add one more number. Now here again we will check, are these two values equal? No, these two values are not equal. So then we will take the value of the element, and now we will make another hop to the index number 2. Now here is the index number 2. So now let me add one more number here. So now we will now compare, these two values are equal. Yes, now these two values are equal. It means this element, the element A, is a root node, is a root element. So to find B, we will get the result as A, right? Why we'll get A? Because A is the representative of this whole set. So A is a representative of this whole set. So now we got A as a result. So here we can say the number of traversal we made is 3. Now let's do another find. Let's say I want to find another element, and I would say find D. Okay, find D. So let's try to implement this method. And where is D? We have, first let's check if the D is here. So the D, the initial element, or the initial index of the D is 4. So now we will go to index number 4, and on index number 4 we will compare these two values, the index and the element. So if it's not equal, then we will make a hop to the element, right? We will go to the index number of that element. So the element is 6, we will go to the index number 6. So here is the index number 6. We made one hop, right? Now we will again do the same procedure and compare these two values. These are not same, then we will make another hop and we will go to the index number 2. We'll go to index number 2 and let's add another number. Now these two values are equal. So and the result will be A again. Why A? Because A is the name of the set, you can say, and it's a representative of the set. So now the number of hops we made is 2. Here we have 2, right? So in the same way, let's try to find another element. Let's try to find H. So when we will do find H, now this time I will use this tree to show you the traversal or the number of hops. It's very easy using this tree. So now the H, where is the H? H is here. The index number of H is 5. So here. So now we will start from H. So from H we will go to G, right? And G is now again pointing to E, E then pointing to C, C then pointing to A. So how many hops we made? We made 1, 2, 3, 4, right? 4 hops. We took 4 traversal. We took 4 steps to get to the element A. So here the answer will be A. The answer will be A, and the hops we made are 4. So as you can see here, that when we want to find any element, the resultant of all the find are the same. The result, we are getting the same result, but we have different numbers we have to traverse from that element to get to the root node or the root element. So it means this, if the answer is the same, then why we are traversing and why this effort we are making. So we can improve this. We can implement a technique using which we need not to make any hops, and we can get a required result in constant time. And that technique is called path compression. Now what is that technique? The path compression technique says that rather than traversing in the tree, connect your elements, connect your data to the root node. Let's take E, right? Now E is first connected to C, and then C is connected to A. So now path compression technique, what it will do, it will connect this element to the root node. So we can connect this element to the root node like this, and now this reference will not be valid because we have changed the reference. So in the same way, what I can do on E, where is E? So here is E, right? So here the first hop is 6. First we will go to 6. It is 6, and now the next hop is 2. We will go to 2. So now 2 is the root element. Now what we will do is we will change this to 2. Right now the E element E is directly connected to the root node. Now if I will say find E, so the result I will get will be A, right? Because eventually, after traversing from E to C and C to A, I will get A for every node. For every node in this set, the result of find will be A. So why then going on, or why we traversing from one element to another to get to the destination? So in the same way, we can change the reference of different elements. Frankly speaking, of all the elements. So now we will change the reference of B, or let's change the reference of H. So let's remove H from here for clarity and create an element H here, and then we can point this element to A. In the same way, we can change its reference. We can create D here. So these positions doesn't matter. I am just showing you with clarity so that I could point these elements very clearly, rather than then I'll have to make a shift from here to here like this. I don't want to make larger lines for this. So now in this way I can connect the D to A also. Now for the G, let's simply connect G to A, right? And for B, I can connect B to A. Let's write B here. So this position is near to the A. So I can say this, right? So now you can see all the elements are pointing towards the root element. And now if I say something like find B, so it's just a constant time operation now, and I can get A as a result. There will be no hops. There will be 0 hops for all these operations. So I can get A here. I can get A for all the operations. So this is called path compression, using which we will get, and we can know that an element is a part of this set. And for getting that answer, we need not to make any traversal. We will get the result in constant time, which is very, very fast and efficient. So I hope this will be helpful for you. And if you did not understand anything, I always recommend and I always suggest to students that if you don't get anything on first attempt, watch the video again. You might have missed something, or you will not be focused while watching the video. So there's no harm in watching the tutorial videos again and again. I will see you in next lecture. Thank you.